is direct evaluation is what it's called. Direct evaluation is something that's going to work if you know that the function is continuous. So if you think about the function 5x squared, what image, just general shape, pops in your head? Parabola. Are there any breaks or holes or anything in a traditional parabola? No. So that function in its entirety is continuous. And if it's continuous, we talked about, the limit at any number is going to equal the function value at any number. So even though they're asking us for the limit as x approaches -3, that's going to be the same as f of -3 in a case like this because it's a fully continuous function. A basic quadratic, always continuous. So direct evaluation would just be plugging in -3. Which is 45, and you're done. Okay? It's a dream when they directly evaluate nicely. They will a lot today because this is what we're learning, but in reality, those aren't the interesting ones to explore, so they're not going to be asked that often because it's just plugging in a number. On the next one, what type of function is this? Let's go back to Algebra 2 for a minute. We have linear. We have quadratic. We have radical. We have rational. We have exponential. We have logs. We have absolute value functions. Any other types? We have trig functions. Sine, curves, cosines, tangents. Step functions. The symbol for that is this like weird thing. It's called the greatest integer function. So you give the greatest integer, whatever x you plug in, the output is the greatest integer less than or equal to that. So if it's 2.9, that symbol around a 2.9 would be 2. Because that's the greatest integer less than or equal to 2.9. Okay? Anything else? Other types of functions. We'll see if any more come up. What is that? Linear. Are linear functions ever discontinuous? No. By the way, I'm going to throw piecewise in there. And piecewise can be a combo of any of these. Could be a piecewise that's 2 linears or 3 linears. It could be a piecewise that's got a linear piece and a log piece. Like it can be any pieces, but piecewise in general. But linears are always continuous. So the limit as x approaches -1 is going to equal the function value at -1, which is just 2. What type of function is this? It's on that list. You had y equals 5x squared, that's quadratic. You have y equals x plus 3, that's linear. You have y equals 2. Linear. That's a horizontal line, yes. Are there any discontinuities in that? Any breaks, any holes? No. So that's a continuous function. You can just plug 8 into it. Of course, there is no place to plug 8 into it because the value will always be 2. And then the last one, y equals x. What type of function is that? Linear. So again, direct evaluation is fine. We'll just plug in 4. We get 4. Okay? Any questions? Whole bunch of properties down here that are obviously heavily laced with symbols and stuff, but this is like a constant function. So really like the example we just did up here. That was a constant function, y equals 2. The idea here is that no matter what x value you're approaching, if it's a constant function, the limit will be that value. Okay? That's this example up above. This is an actual example of it. This is the general format for it. This is a linear function, y equals x. So it's continuous. So if you plug in a, what will you get? Marissa? A. So if it was the limit as x approaches 5 of x, it would be 5. If x was approaching negative 200 of x, it would be negative 200. Okay? If you have a limit that you're looking for, in this case x approaches a, of two functions added together, you take the limit of each one of them separately as they approach that a value and then just add it together. It's not distributing, but I get why it would look like distributing. Okay? You're not technically distributing here. It's just a property that says the limit of two different mini functions added together is going to be the limit of each one individually added together. Same thing with subtraction. Same thing with multiplication. And the same thing as division. Okay? So if you see operations of two separate functions. If it's a function raised to an exponent, like based on the way this one is written, you would take the function and raise it to the exponent first and then take the limit. But this is telling us that you can take the limit of the function first and take that limit value and then raise that to that power, and you'd get the same answer. Especially if it's like a polynomial function, no one wants to raise that to the nth power first and then find the limit. Find the limit first of the function and then raise your answer to the nth power. That's how that works. And then this is pretty much the same thing because the nth root is the same as a power. It's just the 1 over n power. So again, rather than taking the 1 over nth power, we'll take the limit first, and then we'll take the 1 over nth power of that limit. So those are your 8 kind of limit rules that we'll put into play. Okay? All right. So really something very similar to what we just did on the homework quiz, but we want to try to do it without graphing it, right? So is this rational function continuous and defined everywhere? Absolutely not. It's not defined at 2, which is often the limit location that they're going to be interested in. So if you do, let's pretend you do directly evaluate, and you're going to get 0 over 0 if you directly evaluate. This is one of many cases that is considered indeterminate, meaning you cannot determine, that doesn't have an undefined limit necessarily, right? 0 over 0 is an indeterminate case, which means using the method we just used, we don't know the limit yet. It might mean that the limit doesn't exist. It might mean that we just need to go about finding the limit in a different way. So the first thing we're always going to do if we get an indeterminate case, you directly evaluate, you get an indeterminate case. The first thing you're always going to do is try to manipulate the function. And manipulating this function would be the factoring and canceling that we talked about. And that cancels, and it ends up being x plus 2. Once you manipulate, aka simplify, then you retry directly evaluating, and if you get an answer, that's it. Okay? So now I'm going to redirectly evaluate by plugging in a 2. 2 plus 2 is 4. That's my answer. The limit of this function is 4. You really shouldn't have to graph it to get that. Directly evaluate. If you get an indeterminate, try to manipulate and then reevaluate, and you'll have an answer. Sometimes you still won't, and we'll get to cases like that. Okay? So in this particular one, if I directly evaluate, what's negative 1 cubed? What's negative 1 squared times 2 plus negative 1? What's that I'll give you? 0 over. What's negative 1 to the 4th? 1 plus what's negative 1 cubed? What's plus 2 times negative 1? And then plus 2. What's that I'll give you? 0. So an indeterminate case. So we're going to try to manipulate by factoring. So up top, Mitch, what can I do? Good. Anything else on the top, Mitch? Can I go further with this once I've taken out an x? I never group a trinomial 2 by 1. I would do a trinomial by my traditional like algebra 1 ways, which would be like what times what gives you x squared, x and x. What times what gives you a positive 1 such that your outer and your inner will make positive 2. Plus 1 and plus 1, right? So that's the top factored. The bottom factored, because yes, it is 4 terms, does get grouped. So out of my first 2 terms, I'm going to pull an x cubed, and I'll be left with an x plus 1. Out of my next group, I'll pull out a positive 2, and I'm left with an x plus 1. So one term is an x plus 1, and the other is an x cubed plus 2. So we factored. Hopefully something will cancel and simplify. It does. We lose an x plus 1. And then we reevaluate. So I'll plug negative 1 into the simplified version. And keep in mind that factor of x plus 1 that canceled, that was the factor that was creating the 0 on the denominator, right? You plug negative 1 into the x plus 1, you're going to get 0 in your denominator. Now that that's canceled, hopefully that situation is fixed. When I plug in negative 1, what's my numerator? 0, right? Over negative 1 cubed is negative 1. Negative 1 plus 2 is 1. And what's 0 divided by 1? 0. So your limit as x approaches negative 1 on that crazy function that nobody wants to graph, agree? Does anybody want to graph that? Probably not. It would be a rational function still, because even after it, and we have a hole at negative 1, we'd have a squared term on top and a cubic term, so it would be small over big, so we'd have a horizontal asymptote. We'd have some sort of vertical asymptote whenever this equals 0, which would happen at a crazy decimal number. It would be a pretty crazy thing to have to sketch. I'll show you, just for the sake of making sense of it all, what this looks like. So your numerator, x to the 3rd plus 2x squared plus x divided by your other polynomial. Zoom 6, we'll see. So there's where our crazy vertical asymptote is. You see your horizontal asymptote guiding end behavior, but it does look like it came down a little bit and then went back up and then started coming down towards the horizontal asymptote. So that's a little tricky. And if you were trying to find the limit as you approach -1, -1 is somewhere around here. Unfortunately, I'm not going to be able to hit second trace and plug in a value of -1 because there's a hole there. It's going to come up empty. You can't see it, but I can see it. Y equals nothing there. If you wanted to see that same graph, understanding that there is a hole in that graph, you want to see a same version of that graph, you could graph that version of it and do second trace -1, because this one does have a function value of 0 at -1. But the point is, if you look in from -2 to 2 and -2 to 2 on your y, you can see the 0 at -1. Okay, you don't see the hole there, but you see the intention of the graph as it approaches there. Okay? All right. Oh boy. This last, well, this one is the one I really want to make sure we get to. If we plugged in 0, we would get 16 plus 0 is 16, square root of 16 is 4, 4 minus 4 is 0 up top, 0 on the bottom, indeterminate. So, manipulating can mean factoring and canceling like we saw in the 2 examples above. This example of manipulating is totally going to be new to you. So, not totally, halfway new to you. You know how to rationalize, right? Which is getting rid of the radical in the denominator. But there is something called rationalizing a numerator. If we rationalize this numerator, we were trying to get rid of the radical in the numerator. This radical is part of a binomial. So we're going to multiply by this binomial's what? What's that buzzword? Conjugate. So we're going to multiply by the conjugate and watch what happens in the top. When I FOIL, the radical 16 plus x and the radical 16 plus x just becomes 16 plus x. Because they're conjugates, your outer and your inner will cancel, and your last 2 terms will be minus 16. And in my denominator, this is not what I was attempting to rationalize, so I'm going to leave it as x times the conjugate without actually doing it out. And then my numerator reduces to just x. And now you'll see why I did not distribute the x on the denominator. Because the x from the numerator and the x from the denominator will now cancel. So it's 1 over root 16 plus x plus 4. Now I'm going to try to reevaluate. I've manipulated. And I'm going to retry to find the limit. By plugging in a 0, I get 1 over what? What does the denominator become when I plug in a 0? 8. Okay? Manipulating something like this is going to be clearing the complex fractions. So that's something we've done this year. Clear your complex fractions, see what cancels, reevaluate, because this one will also give you 0 over 0 from the get-go. And does anybody want to sketch a graph of that? Probably not. Does anyone want to sketch a graph of this one? Probably not. Okay? So, down at the bottom, just to add on, it's going to be a while before we come across a lot of these, but these are a lot of the cases that are going to be considered indeterminate, that we're going to do a direct evaluation, get any of these, and we don't have an answer. Some of them are kind of tricky, like infinity raised to the 0 power. For so long, you've been told that anything that you raise to the 0 power is 1, but that's not true with infinity. So we'll get there. 1 to any power is supposed to be 1, but it's not. So if you get that when you evaluate, infinities really make things a little weird, and we haven't even touched limits as you approach infinity yet, so we will get there. And then 0 to the 0 power is just as undefined as 0 over 0 is. So those are the indeterminate cases we will come across.